Alright, today we're going to start in on oxidation and reduction reactions. And in order to do that, we need to start defining some things and making sure that we understand them. Alright, oxidation states or oxidation numbers are for an individual atom. And what we use them to do is to indicate approximate electron distribution, primarily in covalent bonding. So even though we've given you this formula of how the electrons are shared in a covalent bond, right? What we really do is we kind of give you some numbers to break up who they actually kind of belong to. What contains covalent bonding? Well, you're either going to have your molecular compounds that are going to be two nonmetals, at least two or more nonmetals. Then you're also going to have your polyatomic ions, which again are still made up mostly nonmetals. There are some metals thrown in there as well, but they at least have a charge on them for polyatomics. Now, they're not real charges since the electrons are shared. It's just kind of a pretend system to try to give a little bit more formality or distribution to it. Now, the shared electron is being counted to belonging to the more electronegative element. Okay, so if you remember electronegativity, this is the whole electron tug of war. So whoever has the stronger power to pull the electrons towards them will get it. And it has a greater attraction for the electrons. The electrons are actually located slightly closer to that atom. And if you remember the periodic trend, it increases as you go up and to the right. So fluorine is the most electronegative element. So remember, fluorine is right here. This is the winner. And then everything goes down from there. So it increases as you go this way on the periodic table. Now, the more electronegative is assigned a negative oxidation state, the less electronegative element has the more positive state. And there are some rules, so you're not going to consistently be trying to figure out what's more electronegative. But if you look at carbon tetrafluoride, fluorine's the more electronegative, so it's going to have a negative number. Carbon is the less electronegative, so it's going to have a positive number. Okay, now we're going to give you some rules for how we actually assign those. Okay, anything that's in a pure element has an oxidation state of 0. It's not really sharing any electrons with any other atom, so it gets 0. Sodium, any of the diatomics, oxygen, and we usually write the oxidation state above the atom, just like that. Okay. Oxidation numbers of monatomic ions alone or in a compound are equal to its charge. So now, opposed, if we go to the sodium ion, it's going to be 1 plus. Actually, the way that we usually write it is our ion charges we write as the number and then the sign, and usually our oxidation numbers we put plus 1. Oxide would be minus 2. Oops. Minus 2. And iron could either be plus 2 or plus 3, depending on what it's paired up with. Okay? Fluorine always gets a minus 1. It's the most electronegative element. Oxygen usually has a minus 2, unless it's trumped by another rule. Except in peroxides, where it has a negative 1. Remember, peroxides are a special type of polyatomic where it's kind of paired together, but it's in an ionic compound. Hydrogen usually has a plus 1, except when it's paired with a metal, it's got a negative 1. For any example, lithium hydride, anything, and when we name it, this is called hydride when it's in a compound like that. All right, some of the oxidation states must equal 0 in a neutral compound, and I know I'm throwing this at you, but the examples will make a lot more sense. So, for example, dinitrogen pentoxide, oxygen is minus 2. Now, one of the things that you have to do is you do have to take into account the elements. So, minus 2 times 5 is minus 10. For nitrogen, there are 2 of them, so each one is going to be plus 5. The way that I normally do the work, which makes sense to me, is I still write it above. So minus 2 times 5 would be minus 10. Now I know the whole thing has to equal 0, so it means that nitrogen's total has to equal plus 10. Well, 10 divided by 2 has got to be plus 5. Okay, and this is the answer up here. These are the oxidation numbers. If you're going to do it this way, it's the numbers at the top of those atoms. Now, the sum of the states of a monatomic or polyatomic ion have to equal the charge of the ion. So nitrate this time, instead of it equaling 0, it has to equal minus 1. Okay, minus 1. So again, your oxygen is minus 2. There are 3 of them. It's got to equal minus 6. Means that nitrogen has to be plus 5. And again, the way that I typically do it, minus 2 times 6. We know the whole thing has to equal minus 1. So your nitrogen has to be plus 5. There's only one of them. And again, this is your final answer. People get confused and think this is it. This is just the math to get the right answer. These are your oxidation numbers. All right, so let's do some practice here. We got about three slides of practice here. And what you may want to do is maybe listen to me do the first one, and then as you go through the second and third, pause it before I give you the answers, try them, and then check your answers. It's probably the most effective way. Okay, so UF6. Fluorine is there's always going to be one, at least one that has a rule. So fluorine is minus 1. There are 6 of them. The whole thing has got to be equal to 0. So uranium has to be plus 6. So these are my answers. If it asked the question, uranium's oxidation number would be plus 6. Fluorine would be minus 1. So again, you got to do the tops. Okay, sulfuric acid. Going to have a rule for at least one. Oxygen's going to be minus 2. Oxygen's contribution is minus 8. Whole thing's equal to 0 because it's not charged. I also have a rule for hydrogen. Hydrogen is usually a plus 1 times 2 is plus 2. So the whole thing has to be equal to 0. There's only one sulfur, so sulfur has to be plus 6. Okay, and these are my answers right here. So these are my oxidation numbers. Oxygen's minus 2, sulfur's plus 6, hydrogen's plus 1. All right, here's the chlorate ion. Oxygen is minus 2. There are 3 of them. Now the whole thing has to equal minus 1 simply because that's the charge on the polyatomic ion. So chlorine has to be plus 5. So again, my answer would be chlorine plus 5, oxygen minus 2. Carbon dioxide, we've got minus 4. Whole thing's equal to 0. So carbon is plus 4. Okay? All right, here's a couple more. Got lots of practice on these. Okay. So if you want to pause it, go ahead and pause it. Try them. All right, bromine is an element. It's all by itself, so it's going to be a 0. Hydrogen is usually plus 1, so it gets plus 3 here. So nitrogen is going to be minus, it's got to be whole thing equal to 0, so it's going to be minus 3. Okay, and again, these are the answers up here. Oxygen is usually a minus 2. So we get minus 6. Whole thing's got to be equal to 0. Now you may be going, do I have a rule for either one of these? Well, I do because calcium is a 2+ ion in this compound. In this compound. So calcium is always going to be plus 2. So then I can figure out that sulfur this time has to be plus 4. So you get different oxidation states in different compounds for certain elements, and sulfur is one of those. Now if we come over here to the hydrogen sulfite ion, oxygen is minus 2, which is minus 6. Whole thing's equal to minus 1. Hydrogen is going to start off as plus 1. So now here my sulfur, plus 1 minus 6. So it's still going to be plus 4 in this compound right here. Oops. And that makes sense because it's still the same sulfite ion. All right, now here was one of the exceptions. Hydrogen is usually plus 1, but here it's paired with a metal. So it's going to be minus 1 and plus 1. We do the math down here, but the whole thing's equal to 0. So there are my answers. Okay, one more if you want to practice or pause it here. Show you the answers. Now over here, this was just to show you the difference between these two. Here is zinc as an element and zinc as an ion. So here at 0, as soon as it becomes the ion, then it becomes plus 2. So the oxidation number changes, and this is going to be important here in just a minute. Now, we have to have a rule for at least one of them. And if there's nothing that trumps it, then we go with typically the ions. So chlorine we're going to do is minus 1. It's going to be minus 3. And nitrogen's, nope, sorry, not plus 5. It's going to be plus 3. So the whole thing's got to equal 0. Then lastly, we've got diphosphorus pentoxide. Minus 10 equal to 0. And the whole thing has to be equal to plus 10, so we get plus 5. And again, these are my answers right here. So oxygen's oxidation number is minus 2, phosphorus is plus 5. Okay, redox reactions is where a reaction in which one or more electron is transferred. Okay, one or more is actually transferred. So for example, for the formation of sodium chloride, we start with a 0 and a 0. And then over here, we get plus 1 and minus 1. Now, if it's in a compound, you want to ignore the coefficient. Okay, so the coefficient doesn't change it. So it still is only plus 1 and minus 1. Now the species losing electrons is said to be oxidized. The oxidation number goes up. The species gaining electrons is said to be reduced because the oxidation number goes down. So if you look at sodium, sodium is going to go from 0 to plus 1, so it is oxidized. Okay, and the chlorine, rather, is going to go from 0 to minus 1, so it is going to be reduced. Okay, it's going to be reduced. Now here are some terms. Like I said, oxidation is an increase in oxidation state, a decrease in the number of electrons, and reduction is a decrease in the oxidation state, increase in the number of electrons. One of the simplest ways to remember that is an acronym named LEO-GER, and we're not going to have to worry about agents at this point. We can cross those off. Excuse me. So this is what we end up doing with these. We write a net ionic equation, determine the oxidation numbers, and identify which substance is oxidized and reduced in the following reactions. So first off, we're going to do copper 2 nitrate reacts with aluminum metal, and I'll see where we are time-wise. We may do propane together in class, but alright, first off I got to write a net ionic equation. So first I have to write my balance reaction and predict the products. Okay, copper 2 nitrate is going to be CuNO3 2. We're going to react that with aluminum metal. Okay, so last time all the ones we were predicting were going to be double replacements. This is a single replacement. So the aluminum is going to kick out the copper. So one of my products over here is going to be copper metal, and then the aluminum is going to take the place with the nitrate. So I'm going to have aluminum nitrate. Aluminum is a 3+ charge, so it's going to be AlNO3 3. Now to get this balanced, I need to put a 3 here, and then a 2 here, 2 here, and a 3 there. Okay, so I'm all balanced now. Now I have to figure out my net ionics. Well, if I look at, and this would say solution, but these two are both aqueous. And obviously if it's a metal, it's going to be a solid. So if I look at this, the only ion, if I split these apart, I'm going to see the only ion that's split up, and it's in aqueous on both sides, is the nitrate. So my nitrate is my spectator ion. Okay, is the nitrate. And then what I'm left with, I have to remember what I'm left with for the ion. So I'm going to have 3 copper 2 ions plus aluminum gives me 3 coppers plus 2 aluminum 3 ions. Now if I look at it from an oxidation reduction standpoint, let me switch colors here just to show you the difference. Let's do green. Okay, copper goes from +2 to 0. Aluminum goes from 0 to +3. So if I identify them up here, just to give me some more space, copper goes from +2 to 0. I always remember it with the oxidation numbers. The oxidation number goes down, so copper will be the one that's reduced, and whereas aluminum, where am I here? Aluminum goes from 0 to +3, so it is the one that is oxidized. Okay, we'll do propane in class 1 because I'm out of space, and 2 because I'm starting to run out of time, so I want to make sure I get this in 15 minutes. Alright, this is just another example. Identify the atoms oxidized and reduced. Here we have a synthesis reaction. Okay, a synthesis reaction where we have aluminum and iodide to form aluminum iodide. Now, if we look at oxidation numbers, you've got 0 for the aluminum, 0 for the iodide at the beginning. They're both elements. This is a little bit off here, but let me do this up here. You've got aluminum, so it would be -1, gets me to -3. Aluminum is +3. So aluminum goes from 0 to +3, so it is going to be the one that is oxidized. And iodide goes from 0 to -1. I know the -3 is down here, but each individual one is a -1, so it is the one that is reduced. And if you think about the electron transfer, because this is what we're going to have to do, remember, losing electrons is oxidized. This one's losing electrons. Gain electrons reduced. So this one is gaining. Okay? I'm going to stop there.